Hi, everybody, and welcome back for Lesson 2 from Unit 6, which is about estimating areas using something called Riemann sums. We have one learning target for today, and that is going to be I can approximate. So we're going to be estimating or approximating a definite integral using a left Riemann sum. So that's going to be one type of estimation method, a midpoint Riemann sum, a right Riemann sum, or a trapezoidal sum with uniform or non-uniform partitions. Now, what we're going to be doing today is learning 4 different ways to estimate the value of an integral when we are unable to find that value exactly using geometric methods. So as a review, the integral from a to b of f of x dx means that we are trying to find the area between f of x, which is the function that's inside of the integral, and the x-axis, between the value where x equals a, which is our lower value, which is our lower bound, and x equals b, which is our upper bound. So the a and the b and the f of x are telling me kind of which area I'm looking for. Sometimes we can calculate those areas using geometric formulas, which is what we practiced in our previous lesson. We could use the formula for the area of a triangle or a rectangle or a semicircle to find these area values for a function. What we're going to learn today is that sometimes we are not able to calculate the exact area using a geometry formula. And the reason for that might be that it's just a non-geometric shape. So it's not a shape like a rectangle or a square or a trapezoid where we could use geometry. When this happens, we use something called Riemann sum approximations. The reason they're called Riemann sums is because the person who kind of invented this method or came up with this method is his last name was Riemann. So these are called Riemann sum approximations, and they come in 4 kind of varieties. There's what's called LRAM, which is a left Riemann sum approximation method. There's RRAM, which is a right Riemann sum approximation method. There's MRAM, which is the midpoint Riemann approximation method. And then there's what's called trapezoidal, which is not a Riemann sum, but is another approximation method. So let's start with our left Riemann sum. So this is the left Riemann approximation method. And here's how this method works. Let's say that I wanted to find the area between this curve and the x-axis over the interval from a to b. So here's my beginning and here's my end. Actually, you know what? Let's make 0 the a. So let's do from a to b. In order to do that, I would need to be able to find the area between here and here using a geometry formula. But obviously in this picture, we don't have a geometry formula for that kind of like a curved shape. That's not a thing we know how to do. So what the Riemann approximation method says, and this is a method, so it's like steps that you follow, is that first we're going to divide this up into sections. So first we're going to take this interval and we're going to divide it into sections. So I'm going to just divide this into sections. Now within each section, we're going to draw a rectangle because we know how to find the area of a rectangle. So for this one, because it is the left Riemann approximation method, we're going to use the left edge of each subsection as the height of our rectangle. Here's what I mean by that. If you look at just this first subsection, there's a left edge over here, and there's a right edge over here. The left edge goes up to here, and the right edge goes up a little bit higher than that. Because this is the left Riemann approximation method, we're going to use the left edge to draw a little rectangle within that curve. Then I'm going to look at the middle section. There's a left edge and there's a right edge. In this case, the left edge is a little bit shorter. Because we're using the left Riemann approximation method, I'm going to use the height of the left side to make a rectangle. And the same thing here, we're going to use the height of the left side of that subsection in order to make a rectangle. And so you can see I've now found 3 rectangles that all consistently use the left edge of their interval to make their height. And if I find the areas of those 3 rectangles, I'm going to get an approximation or an estimate of the total area. Now, in this case, that's going to be a little bit smaller than the actual area because you can see that there's some portions that are not included in our rectangles. But it's going to be what we call an estimate or an approximation. Now, MRAM stands for the right Riemann approximation method. Which means, as you might guess, instead of using the left edge of every subsection to create our rectangle, we're going to be using the right edge of every subsection to create our rectangle. So in this picture, to visualize that, let's say we want to start from A and end at B, and we want to use the right Riemann sum approximation. The first thing we're going to do is divide our area up into subsections. So I'm just going to draw lines. Now for each subsection, instead of using the left edge to create the rectangle, I'm going to use the right edge. You'll notice that in this picture, the right side's a little bit taller than the left side. So I'm going to make a rectangle that uses the right side to create my approximation. Then the same thing for the middle section. I'm going to use the right side to create my approximation. It's going to look like that. And then the same thing for the last section. I'm going to use the right side to create my approximation. Now you'll notice that when I do the right approximation method for this particular picture, all of those rectangles are a little bit bigger than the actual area they wanted. They go outside of the edge of the graph. In this case, we would say that this estimate or this approximation would be an overestimate because it's too big compared to the actual answer. But again, it's an approximation. It's an estimate, so it's okay. It's not exact. It's just a little bit too big compared to the actual answer. The real answer would probably be somewhere in between the pink one and the orange one. The next approximation method is what's called MRAM. So MRAM stands for the midpoint Riemann approximation method. Now, what this means is that instead of using the left side to make your rectangle or the right side to make your rectangle, you're going to use the midpoint to make the rectangle. So we're going to start the same way. Let's say we're integrating from A to B, and you want to find that area. You're going to start by dividing this graph up into subsections. And then, in order to find the midpoint within each of these subsections, you're going to find the height in the middle. Then you're going to use that height to make your rectangles. So you can see that now this is kind of like the best of the options we've looked at because sometimes it's a little bit too big, sometimes it's a little bit too small, and so it's probably going to balance out to be the closest estimate that we have compared to the left or the right side. So it's kind of like a little bit beyond the actual area sometimes and a little bit under the actual area sometimes, so it's probably the best one we've got so far. The last approximation method is what's called the trapezoidal approximation method. Now, this is not a Riemann approximation method because it was not created by the same guy, but it is one of the estimation methods that we need to know. So this estimation method says that you're going to use both endpoints, both sides, to make trapezoids. And this is going to be the most accurate approximation method that we have. So when you're looking at your estimate, this is going to be closer to the actual answer. So first, you're going to start the same way, divide up your interval into subsections, and we're going from A to B. And then here's how this trapezoidal approximation method works. You're going to look at both of these sides, the left side and the right side of each interval, and you're going to kind of connect them. And the reason that this is called a trapezoidal approximation method is that if you look at these shapes that are formed, you end up forming trapezoids as your shapes instead of rectangles as your shapes by connecting the two endpoints with a straight line. So as a reminder, a trapezoid, when we usually look at it, looks like this. But in this case, they're just going to be turned sideways. So it's kind of like the height is there, and then the bottom and the top are turned sideways. So we're turning it into a sideways trapezoid, and that's going to give us our most accurate estimation because you can see it really closely follows that curve. Now let's see this in action. So let's go ahead and go through and try using these approximation methods to find the areas that we're looking for or estimate the areas we're looking for. The graph of x squared plus 3 is shown. Estimate the value of the integral from 0 to 4 using the specified type of approximation method and the number of subintervals specified. So for problem number 1, we are asked to use MRAM, which is the right-hand approximation method, with 4 subintervals. So in other words, take your area and divide it up into 4 rectangles. Step number 1 is to look at your interval. So we are supposed to integrate from 0 to 4. That means the beginning of my integral is going to be here, and the end of my integral is going to be here. So I'm trying to estimate the area in between there. Now, in order to do that, I'm going to start by dividing this up into 4 subintervals because it says I'm supposed to use 4 subintervals. If I'm going from 0 to 4 and I want to make 4 subintervals, I can just count by ones. So that's 1 subinterval, 2 subintervals, 3 subintervals, and the last one's over here. Now, because I'm supposed to use MRAM, for each of those subintervals, I'm going to use the right endpoint to make the height. In that case, it's going to be this taller one right here. So I'm going to make a rectangle that uses that right side to make the height. And then I'm going to use the right side to make the height of my function. And then I'm going to use the right side to make the height of my function. And then I'm going to use the right side to make the height of my function. Now, in order to estimate this area, I'm just going to add up all those rectangles. So my rectangle, my first one, the base is 1, the height is 4, plus the second rectangle, the base is 1, and the height is 6, 7. My third rectangle, the base is 1, and the height is 12. And my fourth rectangle, the base is 1, and the height is 19. And you should have 4 separate rectangle areas here because it told us to use 4 subintervals. So then that means my area is going to be 1 times 4 is 4, 1 times 7 is 7, 1 times 12 is 12, 1 times 19 is 19. So I'm just going to do 4 plus 7 is 11, plus 12 is 23, plus 19 is 42. So my estimate is going to be that the area is 42. Now let's say we want to do something similar, but we're going to use LRAM. So LRAM would be the left side of the interval to make each of our rectangles with still 4 subintervals. So the beginning is here at 0, and the end is here at 4. And I know that because in my integral, that's the lower and upper bound. The first step is to divide this up into 4 subsections because it says to use 4 subintervals. So I'm going to have a subsection here, here, and then here. And then because I'm using LRAM, within each subsection, I'm going to use the left side as the height. That's going to be the lower endpoint now. Be right here, right here. That's the third one, and then this is the fourth one. Now that means I'm going to find the area of those 4 rectangles, which is going to be a base of 1 times a height of 3, plus a base of 1 times a height of 4, plus the base is 1 times the height is 7, plus the base is 1 times the height is 12. And again, you should have 4 areas here because you're using 4 subintervals. Just like before, to calculate my total, since 1 times anything is just 1, I'm just going to add those up. So I'm going to have 3 plus 4 is 7, plus 7 is 14, plus 12 is 26. Now you'll notice this one's too big because all those rectangles went beyond the edge of the graph, and this one's too small, so the real answer should be somewhere in between 42 and 26. Now let's say you want to use MRAM, but this time we're only going to use 2 subintervals. So let's take a look at how you would do that. MRAM, but only with 2 subintervals. So I'm still going to start with the beginning at 0 and the end at 4. And again, that comes from my original integral from 0 to 4. But this time I'm only going to divide this up into 2 subintervals. Now that means I'm only going to divide this up in the middle. So I'm just going to draw one line to make 2 rectangles. In order to use MRAM, from within each of those rectangles, I'm going to use the middle number, which would be right here, to make the rectangle. And then the middle point would be right here to make the rectangle. Now that means that to find this area, I only need to add up 2 rectangles. So I would have a base of 1 times the first height is 4. Oh, I'm sorry, a base of 2 times the first height is 4, because this is 2 units wide, plus a base of 2 times the second height is 12. And that means I'm going to have 8 plus 24, which is 32. Now remember, we said that our answer is probably somewhere between 42 and 26, so 32 is a little bit better, a little closer to our real answer. Last but not least, we're going to practice using a trapezoidal sum with 4 subintervals. So we're going to make 4 trapezoids here. The beginning is still here at 0, and the end is still here at 4. And we're going to divide this up into 4 subintervals so that we can turn each of those subintervals into a trapezoid. So I'm going to draw 4 sections. Now for trapezoids, we're going to be connecting the endpoints. So you can see I'm not using just the left and I'm not using just the right. I'm actually connecting the dots. And you can see here's my first trapezoid, here's my second trapezoid, here's my third trapezoid, and then here's my 4th trapezoid. Now, one thing you may need a little bit of review with is that the area of a trapezoid is 1/2 times the height of the trapezoid, and then times base number 1 plus base number 2. Now, on a trapezoid picture, the height is the distance between the parallel sides. Base number 1 and base number 2 are the lengths of the parallel sides. So in this picture, because our trapezoids are turned sideways, the height is actually the distance between those vertical lines. Base number 1 is the first, like the left side, and base number 2 is the right side. That means that in order to find these areas, I'm going to do 4 different trapezoids. The first trapezoid is going to be 1/2 times the height, which is 1. That's the distance between the vertical sides. And then base number 1 would be 3 plus base number 2 is 4. You can see it's kind of turned sideways. Plus the second trapezoid here would be 1/2 times the height, which is 1. And then base number 1 is 4 plus base number 2 is 7. Plus 1/2 times the height is 1 times base number 1 is 7 plus base number 2 is 12. And then plus the 4th trapezoid would be 1/2 times the height, and then base number 1 is 12 and base number 2 is 19. I'm sorry, plus. There we go, plus. There we go. All right, so to figure this out, I'm going to do some calculations here. I'm going to deal with the 1/2 in a second because everything is multiplied by 1/2. So you can think about that as factoring out the 1/2 of every one of these trapezoids that I'm going to be adding up. So I'm factoring out the 1/2 so that I can divide at the end. 3 plus 4 is 7, plus 4 plus 7 is 11, 7 plus 12 is 19, 12 plus 19 is 31, which means I'm going to have 1/2 times 7 plus 11 is 18, plus 19 is 37, plus 31 is 68, which means I get 34 as my final answer. And that is probably going to be the best guess that we have for our final answer because it's closest to following the function. Okay, what if we're given a table of values instead? So what if instead of given a graph, we're given a table of values? In this problem, we are asked to estimate the integral from 0 to 9, so starting from 0, which it turns out is the beginning of our table every single time of our x values, and ending at 9, which it turns out is the end of our table. Now, I will warn you, we don't always go from beginning to end of the table. I just want to show you that in this case that does happen using the specified approximation and the given number of subintervals. One option is to sketch a graph, but I'm going to tell you sketching a graph here can be very time consuming, and honestly, it's hard to be accurate when you're doing a sketch, especially without graph paper. So I have a strategy and kind of an organizational method that I'm going to teach you to help you organize your thinking so that you can find these approximations. Here's how we're going to do this. If we want to use our RAM, which is the right side, with 4 subintervals, then we know that ultimately we're going to have 4 rectangles. So what I would do is I would draw 4 little lines. 1, 2, 3, 4. We have 4 little rectangles. Those are our 4 little bases. Now the x values on the graph are what determine the width of the rectangle. If you go back to how we drew this picture, the x values determine the width. Start from here, go to here, it's 1 unit wide. So we're going to use our x values from our table to label the widths. The first rectangle would start where x is 0 and then end at 3. The next rectangle would start from 3 and end at 6. The next rectangle would start from 6 and end at 8. And the last rectangle would start from 8 and end at 9. So again, I'm using the x's to label the width of the rectangle. Kind of like if you're imagining that's like a number line, you're labeling it. Now we want to find the heights. In this case, since we're using our RAM, we only care about the right side of each of these intervals. And so I'm going to draw a little vertical line. You can imagine that that's kind of like the height of the rectangle if you were to look at the graph. The reason I'm drawing that vertical line on the right side is because that's going to help me figure out which of these y values to use as the height of that rectangle. You'll notice that in this interval, the vertical line is above the number 3. That means that on the right side of that interval, we would be using the 5, which is the y value that goes with the number 3, as the height. So I'm going to label that height of that rectangle would be 5. Above the number 6, I would label that height would be 4. 8 would have a height of 6 and 9 would have a height of 8. So if you were to graph this, it would be it would go 5, 4, 6, 8. You would see that visually. Now, each of these represents one of the 4 rectangles that you're going to find the area of in order to find your estimate. So the first rectangle would have a base width of 3 because from 0 to 3 is 3 spaces. So base would be 3 times the height would be 5. The next rectangle would have a base width of 3. So the base would be 3 and the height would be 4. The next width would have a base of 2. So the base would be 2 and the height would be 6. And the next rectangle would go from 8 to 9. So the base would be 1 and the height would be 8. So this is like a visual, like an organizational tool to figure out these rectangles without really sketching a graph. You're just kind of visualizing the rectangles using numbers. Now I'm going to find those areas. So 3 times 5 is 15. 3 times 4 is 12. 2 times 6 is 12. 1 times 8 is 8, and then I can add up all 4 of those areas. So I'm going to do the 8 plus the 12 first, that's 20, plus 15 is 35, plus the other 12 is 47. Now let's say we wanted to use the same table, but we want to use LRAM with 4 subintervals. So because there are 4 subintervals, I'm going to draw 4 little lines. Now, the first subinterval goes from where x is 0 to 3. Then we're going to go from 3 to 6. Then we're going to go from 6 to 8. And then we're going to go from 8 to 9. So there's my 4 intervals, 0 to 3, 3 to 6, 6 to 8, 8 to 9. Now this time we're using LRAM. So when we imagine these rectangles, we need to imagine we're using the left endpoint height in order to make the height of the rectangle. So you'll notice I drew my vertical line on the other side this time. That's because I want to remember that the height of this rectangle should be the y value that corresponds to 0. So this height is going to be 3 because 3 corresponds to 0. Then I'm going to use the 5 because that corresponds to the x value of 3, then 4, and then 6. So I'm kind of visualizing those rectangles. Then I'm going to find each of those areas. So the first base would be 3 times 3 is the height, plus the next base would be 3 times 5 is the height, plus the next base would be 2 times 4 is the height, and then the last base would be 1 times 6 is the height. And I'm going to find those areas and I'm going to add them up. So I'm going to have 9 plus 15 plus 8 plus 6, which means I'm going to get 8 plus 6 is 14, plus 15 is 29, plus 9 is 38. Next, we're going to use trapezoidal. So for our trapezoidal method, that means that we're going to have 4 trapezoids. Now for a trapezoid, we have 1, 2, 3, 4. We're going to start the same way, kind of visualizing the x values and how they'd spread out around the x-axis. So be 0 to 3, 3 to 6, 6 to 8, 8 to 9 would be our x value chunks. So we'd have like 0 to 3, 3 to 6, 6 to 8, 8 to 9. But for a trapezoid, we learned we use both sides to make a trapezoid. So in these pictures, I'm just going to go ahead and I'm going to draw both the left and the right. And it doesn't matter which one you make taller, which one you make shorter. It's just to help remind you that this is a little trapezoid that's been turned sideways. So now I'm going to label both heights. So 0 corresponds to 3, 3 is 5, and then I have 5 and 4, 4 and 6, 6 and 8. And like I said, it doesn't matter which one of those sides is taller or shorter. You're just labeling it so you can visualize the 2 bases in the area formula for the size of a trapezoid. So the area formula for a trapezoid would be 1/2 times the height. In this case, the height is, as we said before, like the distance between those vertical lines. So that would be 3. And then base number 1 plus base number 2 would be 3 plus 5. Plus 1/2 times the height. In this case, that again would be 3. And then base number 1 plus base number 2, so 5 plus 4. Plus 1/2, and then the height would be 2. And then base number 1 plus base number 2 is 4 plus 6. And then the last trapezoid would be 1/2 times the base would be 1. Sorry, the height would be 1. And then base number 1 plus base number 2. 6 plus 8. So those are my trapezoids. Now all of those are multiplied by 1/2. So I'm going to deal with that in a second. I'm going to put that on the outside. Imagine that's like factoring it out. 3 plus 5 is 8 times 3 is 24. Plus 5 plus 4 is 9 times 3 is 27. 4 plus 6 is 10 times 2 is 20. 6 plus 8 is 14. And that means that I'm going to have 20, 40, 60, 70, 4, 8, 85. So I'm going to have 1/2 of 85, which is just 85 over 2. or it could be 42.5. Now, last but not least, I am not going to ask you to use a midpoint sum, and I'm going to tell you why. Midpoint requires us to be able to find the number that's in the middle. We don't know, because this is a table, which number is happening in between 0 and 3. The middle number would be 1.5. That would be halfway. We don't know what the height is at 1.5. So we don't know the output values for the midpoints here. And so we can't use a midpoint estimate because we don't have enough information. Last thing that we're going to talk about today. When you are estimating, the number of intervals you make matters. When you're using LRAM, RRAM, MRAM, or the trapezoidal approximation method, we do not get the exact answer. We're getting an estimate. And our estimate can be better or worse depending on the size of our subinterval. The subinterval is how wide you make your shapes. So you'll notice that here there are 3 subintervals. And here there are 1, 2, 3, 4, 5, 6, 7, 8 subintervals. Your estimate using this many subintervals is going to be better than using 3 because there's less extraneous area. You can see there's a lot of extra area you're getting here when you find the area of these rectangles. There's less and less of it the more subintervals you make. So smaller subintervals means you get a better estimate. That means the smaller you break up your area into and you find lots and lots and lots of different rectangles or lots and lots and lots of different trapezoids, the better your estimation for the actual exact area is going to be. All right, that is it for today. Thank you guys so much for watching. And